In how many ways might we calculate the central area? This problem gives me the opportunity to show how to set up the problem using calculus and trigonometry, to check out whether or not there exist substantial differences if we carry out our calculations exactly or numerically, and some principles to use for mathematical problem solving. To solve the problem using trigonometry, consider the following picture and focus on the quarter of circle with radius KD first. Due to the picture symmetry, it is easy to see how arc AC first is made up of 6 equal shorter arcs, namely AL, LE, EK, KF, FM, MC first. We will not mathematically prove it, of course, but if you want, you simply need to show that all the subtended chords are equal. Since these chords are equal, we can easily calculate the sectors related to each of these arcs. Mathematically, the sector enclosed by KD first F is expressed by this relation. We are interested on this sector because it contains the area of the triangle KOF, which represents 1/8 of the target area. To calculate this target area is therefore necessary to first calculate the area of triangle OD first F. This calls on us to determine the length of segment OI, which represents the height of the triangle. This is calculated using trigonometry by this relation, where 15 degrees stems from recognition that the angle in blue is the sixth part of a right angle. Therefore, the area of triangle OD first F will be expressed by this relation. Finally, the target area will be 31.51. The second solution involves calculus, and we will rely on the following picture to calculate the target area and compare it thereafter to that obtained through trigonometry. I will exploit the area identified by the points OFG. More specifically, I will obtain this area by subtracting from the area of rectangle OF F1G1 the area subtended by GF arc. To calculate this area, consider an infinitesimal rectangle of area fx dax as shown in the picture. Since we need to compute an integral of fx on the interval g1 f1, we need to express their coordinates. While g1 component along x-axis is already known, f1 component along this axis can be obtained by determining the intersection at f between two circles equations. The required value is near 87% of the square side. Thus, the area subtended by GF arc will be given by the following integral, and the area identified by the points OFG will be 7.9. Multiplying this value by 4, we will get the target area, that is 31.64. Is there any difference between the exact and numerical solution? Why does this value differ from the one obtained using trigonometry? The error, which is given by 0.41%, is due to the numerical calculations performed in the last steps. The importance of this fact stems from recognition that as long as you deal with problems that lend themselves to the derivation of exact solutions, then you should strive for achieving this. Also, this fact reminds us that the key role of round-off error that tends to propagate through floating point operations, thereby affecting the final result. For the sake of completeness, the exact solution for this problem is given by this formula. With this in mind, which principles should we be aiming for whenever we try to solve a problem? One of the first most important key steps in problem solving involves restating the problem in as many ways as possible. What does this specifically mean? For the problem we have just solved, it means to seek out alternative ways of expressing the target area. As the picture shows, the target area is restated as 8 identical areas, one of which, that identified by points KOF, was obtained using the knowledge of the sector and blue triangle. In the second solution instead, We have restated the problem into the specific problem, calculate the fourth area identified by points O, F, G. Hence, the purpose of restating the original issue is to seek to derive a specific problem that calls on us to solve smaller chunks. The smaller chunks might require the application of a theorem, a technique, or a concept. A third way in which we might have restated the same problem in a different way involves algebraic steps. Consider the following picture. If we indicate the central area as Z and the smaller one X, it turns out that both are related by the following equation. However, this problem is indeterminate because we have more unknowns than equations, and we no longer can rely on algebraic approach. Another key principle is what I call estimate beforehand. Estimating beforehand answers the important question, how do we do to know whether our solution is correct? How do we know if we are proceeding correctly? In this case, there exist two ways of estimating the solution before working out the problem, and both of them entail determining a lower and an upper bound. In science, bounds play a key role. Just to name a few of such relationships, we remember the Cauchy-Schwarz inequality, the Hölder inequality, the Hilbert inequality, and Hardy inequality. To determine a lower and a upper bound for the target area, we might split the whole square of length r equal 10 into tiny squares of known area as shown in the picture. By counting the number of inner and outer squares, we quickly obtain the following bounds. As we can see, the area we have calculated using two approaches resides within this range of values. A second, more precise way of estimating beforehand the answer involves the construction of a square, as shown in the picture. Using this approach, for instance, the estimated lower bound is 27.04. Here the takeaway is, if you find an alternative way of looking at the problem, you increase the odds of identifying a more simple procedure. This is true for a mathematical problem and any other problem encountered in engineering and physics too. Also, try to figure out whether or not you're making a progress toward the goal by estimating beforehand.